So, in the previous classes we have looked at important properties of the gas dynamic flow, which is the stagnation properties and the star properties. So, to get the concepts clear, we will do 3 numericals now and look at various aspects related to stagnation and star properties. So, to just to recap, the stagnation conditions can be defined at any point in the flow, and they are achieved by a isentropic process going from that particular velocity, pressure and temperature conditions to a condition where velocity goes to 0, and this is achieved isentropically. And using the energy equations and the isentropic relations, one can relate what happens to temperature and pressure at stagnation conditions. Those conditions are referred to as stagnation temperature and pressure. Then the counterpart of that is the star or the sonic conditions. In this, the flow is taken to a state where the velocity of the flow is equal to the acoustic speed at that particular point. So, that is at that point. So, that Mach number is equal to 1. So, whatever be the Mach number of the flow at that particular point, through an isentropic process you take it to a Mach number which is equal to 1, and then the properties that you calculate at that point is known as the sonic conditions. And in an adiabatic flow, both the stagnation and the star properties remain constant, and that is something that is going to be widely used while solving problems. So, that is the basic concept. So, now let us look at the numericals. The first example here is an aircraft flies at 800 kilometer per hour at an altitude of 10 kilometers. The air is isentropically compressed in a diffuser. If the Mach number at the exit of the diffuser is 0.36, determine the entry Mach number, B, velocity, temperature and pressure of the air at the exit of the diffuser. So, see, there is a example where an engineering device known as the diffuser. So, a diffuser is any device which reduces velocity, and consequences of that is that pressure and temperature increase, and this we have seen even in our discussions in the isentropic relations, that when it is decelerated, pressure and temperature will increase. So, so these are present in many devices, and this is a typical example. So, here the way to begin with is you are given the altitude. So, again some concepts that become important here is the flight velocity, and altitude is given. So, static conditions and stagnation conditions, the distinction between them. So, once you know the altitude, you can reference to a standard atmosphere and get the pressure at those altitudes. So, the pressure is P infinity, this is 0.264 bar, and temperature, which is T infinity, is 223.15 Kelvin. So, this we can easily find out by using a reference atmosphere. Then we are given the velocity of the aircraft. So, aircraft velocity is given, that is V infinity. This is given in 800 kilometer per hour. So, this can be converted to meter per second, the SI units which is normally used, and the conversion is this turns out to be 222 meter per second. So one should notice here that the temperature is quite low, and you can expect the velocities the velocity is significant, so you can expect compressible effects here. So first thing to do here, as we know in our relations of stagnation conditions and static conditions, that everything is dependent on gamma and Mach number. This is air, so gamma is 1.4. So the way to do this is to connect the given quantities to the stagnation quantities, and then from there come to the exit of the diffuser. Since the flow is isentropic, the stagnation pressures and stagnation temperature do not change within the flow. So once this is sort of understood, then it is easy to go ahead with the solution of this problem. So first point is we have to get the Mach number for this flow. So for Mach number is V by V infinity by A infinity, that is the Mach number of the flight. This is given 2.2 divided by square root of gamma RT, which is 1.4287, and temperature is the static temperature at that condition. So it is 223.15, and this Mach number, if you do the calculation, it will come out to be 0.742 is the Mach number of this flight. So this is known. Now we have to get the relation between what is P naught 1. So P naught 1 and T naught 1. The idea is at the exit of the diffuser. So diffuser is for this is a subsonic flow. So you have a diffuser something of this kind, which, so this is the entry where it is coming in, and conditions are known here. Mach number is 0.742, P1 T1 is known, and P2 T2 and should be found when M2 is known to be 0.36. So this is known to you. So and the flow is isentropic, so P01 and T01 remains constant. So we have to find what is P01 and T01. The way to do this, as I had discussed last time, is that once you know the Mach number and gamma, you can calculate this from the relations. P0 by P is 1 plus gamma minus 1 by 2 m square whole power gamma by gamma minus 1. You can use these relations, calculate this over computer or using a calculator. This is quite simple, so it is you can do it over a calculator, or you have tables and charts for this which can be used, or you can use also an online calculator where you can feed in the gamma and Mach number, and you can get results for what is usually the results will be in terms of P by P naught and T by T naught for a given gamma and Mach number. So this can be easily found out by various means. You are free to choose the means, and what you can do then is get P by P naught for this given Mach number. In this case for 0.742, P by P naught turns out to be 0.695. So that means P is known, and So P naught will be P divided by this value 0.695, and P is already given at 0.264. So this is 0.264 divided by 0.695, which is 0.38 bar. Now for stagnation temperature also you can go ahead with similar formulation. You can find out T naught by T. The other way, once you know directly you know the velocity, the other way to get T naught is using the equation T plus V square by 2 Cp. For a calorically perfect gas, you can use this equation also, and here all the quantities are known to you. So this is 223.15 plus 222.22 square divided by 2 Cp, and T naught turns out to be 247.72 Kelvin. So now you know P naught and T naught. Now getting to the exit is straightforward. These quantities remain the same, P naught and T naught. So now Mach number has changed to M2 is 0.36. Now again for this value of M2 one has to find out what is P naught, P by P naught, and T by T naught. If we find this, then it is you can multiply the equation. So for 0.36 M2 equal to 0.36, so P by P naught is 0.914, and so you can get P2 is P naught is 0.38 multiplied by 0.914 equal to 0.347 bar. Similarly, T by T naught, T by T naught is 0.975. So T2 you can get it multiplied by 247.72. This will be 241.53 Kelvin. Now what we need to do is now find the velocity, that is V2. We are given Mach number M2, so we can get velocity V2 is M2 multiplied by A2, the speed of sound at that particular point. Speed of sound is a local variable, so you have to calculate the speed of sound at 2. This is different from what it was at 1, and A2 is square root of gamma r T2, and T2 you have found out here in the previous step, and so you can substitute that here, 287 into 241.53 and multiply this by Mach number. So this turns out to be 311.52, and V2 is just multiply 0.36 to this value, and you get V2 as 112.146 meter per second. So this example sort of showed you how the concepts of stagnation pressure, stagnation temperature can be used to quickly estimate flow properties at different points in the flow path. In this case it was a diffuser and it had an isentropic flow through the diffuser. So For the first estimate, this is a very good way to calculate these flow properties. Now let us go to the second example. In the second numerical example, air at 400 Kelvin temperature exits a duct as a jet at sonic velocity. So here it is given that the temperature of airflow is 400 Kelvin and it is at sonic conditions. That means we know what is sonic condition. At the exit of the duct, Mach number equal to 1. So Mach number at exit is equal to 1, gamma is given, R is given 1.4 and 287. Now determine velocity of sound at 400 Kelvin, velocity of sound at stagnation conditions, maximum velocity of jet possible, stagnation enthalpy. So here now the velocity of sound at 400 Kelvin is the same as the velocity of jet, because you are having it at critical conditions, that is V star is equal to A star. So this at sonic speed. So velocity of sound here at the exit is the same as square root of gamma R TE, which is 1.4 multiplied by the temperature 400 Kelvin, and you can find out this turns out to be 400.89 meter per second. Now next is what is the speed of sound at stagnation conditions. Now this is also since T naught is an important parameter, that is the stagnation temperature, you can calculate the velocity of sound at stagnation conditions at stagnation temperature, that is the stagnation velocity of sound, or you can, that is given by, you can use from here you can go in very different methods you are possible, all are equivalent. One is to use the charts to the speed, for this its Mach number is 1, and the relationship between the P by P naught, T by T naught at Mach number equal to 1 is known, and then you can find out what is T naught, and from there get A naught. But another sort of straightforward method is directly using the alternate form of the energy equation, which is A square by gamma minus 1 plus V square by 2 is equal to A naught square by gamma minus 1. This is directly from the alternate form of energy equation, and here for stagnation conditions the velocity is 0. So this is the equation, energy equation. So here both V square and A square is known because they are the same. So this is turns out to be 2 gamma minus 1 A star square is equal to A0 square by gamma minus 1, or from this you can write immediately that A0 square is gamma plus 1 by 2 A star square. So this gives you directly the relation for A naught, because A star is known, you have already found it out. So A naught turns out to be 439.15 meter per second. Then the next question is, what is the maximum velocity of the jet possible? Now here also we can use the energy equation to get to this number. The idea here is that if you look at the energy equation for an adiabatic flow, v2 square by 2, you can see that any change in velocity involves interaction between the enthalpy and energy, kinetic energy. So it is a balance between the enthalpy and kinetic energy. What if we ask the question, what is the maximum velocity that is possible, then there are two, that the answer is simply that if all the enthalpy and internal energy gets converted only to kinetic energy, then that yields the maximum velocity that can be extracted from the flow, that is V max. That is the concept here. It is directly it's the in the other way, if you look at it, if you take the flow to 0 velocity, then all kinetic energy is getting converted to flow enthalpy. So that is the stagnation enthalpy. So we can relate that. So this is stagnation enthalpy H naught, and this is equal to, in the second case, this goes to 0. So this goes to V max square by 2. This is the maximum enthalpy that can be taken in. So, and since this H naught can be expressed as Cp T naught, and we know this can be expressed as A naught square by gamma minus 1 V max square by 2, then already this A naught is determined in the previous calculation. So V max is A naught square root of 2 by gamma minus 1 multiplied by A naught, and this turns out to be 981.97 meter per second. So this is the concept of maximum velocity, and finally we have to determine the stagnation enthalpy. This is H naught. H naught is a stagnation enthalpy. It is Cp T plus V square by 2. Okay. Here temperature is T star, velocity is A star. This is already known, and it is calculated. So this comes out to be 1005 multiplied by 400 Kelvin. V star is known, is also is 400.89 by 2, and this results in 482.35 kilojoules per kg. So we have determined the various. So here a new concept that came about in this numerical is that of maximum velocity through an isentropic process, and this is determined when all the enthalpy, total enthalpy, gets converted only to kinetic energy. So another example similarly using for a particular device is 3. A ramjet flies at 11 kilometer altitude with a flight Mach number of 0.9. Combustion takes place at constant pressure and temperature, sees an increase of 1500 degrees centigrade. So temperature increases by 1500 degrees centigrade, but during combustion pressure remains constant. Combustion products are then ejected through the nozzle at inlet pressure and temperature. are 0.3 atmospheres and 213 Kelvin. So, inlet pressure and temperature is given, exit pressure is 0.3 atmospheres, that is also given. So, let us take it as a box, and what is given at the inlet pressure is given 0.3 atmospheres, and temperature is given 213 Kelvin, and at the outlet, that is, this is 1 2 at the outlet, you are given exit pressure is 0.3 atmospheres, this is given, and here you are given pressure is constant, while temperature increases by 1500 degree centigrade, it is the same as Kelvin. So, 1500 Kelvin. Calculate stagnation pressure and temperature, calculate the exit velocity, what will be the critical values of pressure and temperature. So, here assumption is that pressure and temperature brought to stagnation conditions inside the combustion chamber isentropically from the diffuser. So, the diffuser, again it is an isentropic diffuser, and it is taking so flight Mach number is given 0.9, and is taking that and converting it isentropically to the combustion chamber conditions, and their pressure is constant. So, let us solve this. You are given P1, that is inlet pressure is 0.3 atmosphere is given, and T1 is also given, 213 Kelvin, if that was correct, yes, 213 Kelvin. So, and Mach number is given, Mach number of the flight is 0.9. So, now directly use the relations P by P naught for Mach number of 0.9. Mach number is 0.9. If you get this, this value is 0.5913. So, from this P naught is calculated, it is 0.507 atmospheres. Next is what about temperature T by T naught. So, here T by T naught at 0.9 is given 0.8606. So, T naught goes to 247.5 Kelvin. So, what is given? The given it is given that the increase in temperature is 1500 Kelvin. Now, diffuser decreases the velocities to very low values. So, one can unless otherwise stated, since there is it is not really stated, what is assumed here is that the diffuser brings down the velocities to low values inside the combustion chamber. So, if it is low values, then its pressure and temperature is almost same as that of the stagnation pressure and temperature. This is something we refer to as the reservoir conditions. When velocity is very low, then its pressures and temperatures are very close to that of the stagnation pressure and temperature. So, we can use that assumption here and find out that what is the final temperature. So, T final, that is T exit or T naught exit, because it is the total temperature. So, you are adding 247.5 plus 1500, this is 1747.5 Kelvin, and now the final temperature is known, and pressure remains constant here. So that is given, it remains constant at 0.507 atmospheres. Now at the exit the pressure is given as 0.3 atmosphere. So this is very special case of very ideal kind of analysis. So in real analysis there will be other irreversibilities that come into picture. So so here then we can use, we know the pressure ratio here, that is P by P naught is known. Okay, so this turns out to be 0.5917, and as a consequence it is similar to what we started with this. So m exit is 0.9. Yet what is the velocity at exit? So now you see that the temperature has increased. As a consequence of this, the speed of sound has increased. The T by T exit, that is T by T naught, for 0.9 we already know this, we had done it already, and from there you can calculate what is T exit. So you can calculate T exit, which turns out to be 1506.345 Kelvin, and from here you can calculate the V exit by using either you can use the conditions that you relate T naught, that is H naught is equal to H plus V square by 2 Cp. You can use this, or the other way to do it is find out the speed of sound for this particular temperature, static temperature, and then find out velocity. So then V exit will become 696.21 meter per second. Now for to find out critical conditions, what are the critical conditions? So this you can directly use the relation between P star and P naught is gamma by gamma minus 1. Similarly T star by T naught is 2 by gamma plus 1. So you can and T naught and P naught is known. So this turns out to be 0.2678 bar, and here this turns out to be 1456.25 Kelvin. So I think with these three numerical examples we can sort of look at, we have a clarity on the understanding of stagnation pressure and stagnation properties and star properties. So with this understanding we will move on to normal shocks, where these concepts will be used extensively to analyze the normal shock itself. So that we will start from the next class.